Start recording. Dmitry, you're on.
Oh, thank you both. So, does everybody hear me?
You're
Okay.
you're perfectly audible.
Okay, thank you. Welcome, everybody. Um, so, today I'm going to talk about multithreading in Krita. When rehearsing this presentation today, I found out that it might be a bit too much information for a single presentation. So it might be a bit too much information. And if you have any questions, don't hesitate to stop me or interrupt me and ask your question if you don't understand something. I think in this blue button interface, you can do it either by writing a question in your chat or raising your hand in the status of your user. You should right click on your name. Oh no, left click on your name and set status, raise your hand. But I think it would be easier just to write the question to the chat, and I will try to follow it. So my presentation have 5 parts. In the first, I will tell a few words about Tiles Data Manager. This is the base where all pixel information is stored in Krita, and how this data manager, what this data manager requires from multi-threading point of view. Then I'll talk about different types of jobs, of multi-threading jobs we have in Krita. Then I will talk about updates queue, about strokes queue, and in the end, it will be probably the most complicated part. I will try to show you an example how one user action works. Image color space to another color space. It is also multi-threaded, so it's rather funny example, but a bit complicated. So the first part is about data manager. As you may know, Krita doesn't store the image in a consecutive memory. Instead, it splits the image into small tiles of 64 by 64 tiles, or 64 by 64 pixels. And all these pixels, all these tiles are stored in KeyStyle Data Manager, which is stored in KeySpain device. And all of us use KeySpain device all the time. So Data Manager supports multi-threaded access to pixels in it with only one limitation. And so this is kind of rule of thumb. When you access Paint device or Data Manager, one pixel of this Paint device may be written by exactly one thread at the same time. It means that you can read whatever part of the image or whatever part of Paint device from as many threads as you like, but you can write the same area only from one thread. I'll show you some examples. I think you can see a pointer here, the red dot. So we have 2 threads which write to different areas of the same Paint device. These threads can do whatever they want inside the area. They can read or write. It is perfectly safe. Data Manager will handle it, even without any blocking inside. Well, yes, that's okay. So even if we write into two, read or write into two neighboring pixels, it will also be safe, even if they are stored in the same tile or something like that. The developer should not worry about that. If we are not writing into the same pixel, it is safe. So if we are reading from the same pixel from different threads, it is also safe. And this case is a bit tricky. And another thread reads from this pixel. This is also safe, but it might be a bit tricky, as you may guess, because in this example, thread 1 will write its data into the pixel correctly. It's not a problem. But what will thread 2 read from this pixel if he tries to read from this area at the same time? It is not defined what it is going to read. It may read the state of the pixel before write operation. It may read the state of the pixel after write operation, or some incomplete data. From data manager point of view, this state is completely valid, and it is valid on purpose because we use this undefined behavior a lot in Krita. As you may as you may remember, at the last sprint, we saw a bug if when Divat was painting on the canvas with a very big brush on a huge screen. You could see that updates are coming in rectangles. The brush painted not in circular shape, but updates came in small rectangles. That was exactly because of these incomplete read operations. The point is, it is done for performance sake. We have two different queues. One queue, in this example, it will be thread 1. This is a strokes queue. This thread actually paints with a brush on a paint device. And in another queue, in updates queue, another thread, this one, will read from the same paint device to render this stroke on a final projection and show it to the user. So these two processes happen at the same time, and it may happen that update thread, this one, will read from this area while the brush paints in this area. It is not beautiful, but it lets us not block rendering process when showing it to. That's what we have, and that's what we use a lot. So you should not be scared about that. And the last example is when two threads write into the same area. This state is completely invalid. No two threads should ever try to read into the same area or specifically into the same pixel. The problem is that data manager that stores data, which handles swapping on the hard drive, lazy copying, and all that, this data manager cannot catch this situation when two threads are writing to the same area, and it cannot work around it even. So if you try to write into the same pixel, you will most probably you will get a crash. It will be a segmentation fault or some assert somewhere deep inside the data manager. Well, this is invalid, and you should never try to do that, and you should care about not writing into the same area on the same paint device at the same time. just concluding it as a simple rule, if you write new code that does multithreading and which accesses the same paint device in different threads, and you see a crash somewhere deep in Tiles data manager, it's probably you are trying to write into overlapping areas. So you should search for you should search the problem not in the data manager, but in your own code that tries to write incorrectly. So this rule again, one pixel must be written by exactly one thread. It's easy to state this rule, but it's very difficult to follow this rule. Because, for example, in Krita, canvas updates may run in parallel on different areas, and we need a special scheduler that ensures that no two updates try to update the same area at the same time. Because if they try to update the same area, they will try to write into the same area, and they will crash Krita. So that was a quick part about Data Manager. Do you have any questions so far? I don't think so. Oh, someone is tapping? Okay, good. So, multithreading in Krita, it's probably a bit wrong title for this slide, because I'm going to tell you about different APIs and different kinds of jobs we have in Krita and we use in Krita. Where is it? So the first type of jobs that can be executed in the scheduler are layer stack updates. You usually start them by calling layer set dirty or image refresh graph async. If we speak in terms of OpenGL, these jobs are fixed pipeline. Oh, Daniel, do you have any question? Okay, it is not a problem. Basically, I was talking about keyspain device class. You might have seen it already, or you can check it later. It's the basic object that is used for storing pixel data. So the only thing you should know about it that you should never write to the same area from different threads. That's the main conclusion that you should take from the first part. Okay, so layer stack updates. In Krita, we have two independent queues of jobs. The first is updates queue, and the second is strokes queue. So layer stack updates are these jobs are generated every time you call layer set dirty or refresh graph async. They are fixed pipeline jobs. That is, you cannot modify this job. If you told that when you call layer set dirty, you declare that this area of layer became dirty, and it should be integrated into it should be integrated probably into the final projection of the image and should be shown to the user. When you call refresh graph async, you show that well, this area of layer became dirty, and this area and all subgraph of layers should be regenerated and showed to the user. I don't know what to say about that more. Well, both of these actions are asynchronous. That is, when you call layer set dirty, you just put a task into a queue, and this update will happen sometime later. You are not guaranteed to get it anytime soon. So the second type of updates, the second type of jobs are spontaneous jobs. These jobs are also updates. That is, they are running in updates queue, not in the strokes queue. In contrast to layer stack updates, you can create your own jobs. So you cannot, when calling layer set dirty, you cannot modify the job that is added to the queue. But you can create your own spontaneous jobs, and we use it a lot. We use it for example, to generate selection outline. What else do we use it for? To generate selection outline, we used to use it for generating projection of generator layer. Since recently, thanks to MSpark, it's changed. Now it uses strokes for that. But the main point about spontaneous job is just like it works like queue runnable. If you're familiar with Qt concurrent framework, so it's basically some runnable job that you can run on a scheduler as a single job. The main difference from queue-runnable is that spontaneous jobs are mergeable. That is, if you look at the example of generator layers, if you have generator layer dialog open and you changed your configuration like 3 or 5 times, and the dialog generated 3 or 5 spontaneous jobs, which would have to regenerate the generator layer. Due to well, spontaneous jobs have a special method that would let the scheduler to merge all these 5 jobs into one single job, and basically only the last job will be executed, and all the previous 4 jobs will be just dropped, because you don't need to regenerate generator layer if the user has already changed the config and it is not valid anymore. The third API we have is called strokes. You surely heard it a lot of times. A stroke is an abstraction for a user action that is some complete finished user action. In the end of the stroke, almost all the strokes create a single undo history item. So basically, when you drag your stylus on a tablet, you create one stroke. When you sorry? MSpark? What? Okay. Okay, so we create a stroke when we want to execute a complete user action that will that would land in undo history. Strokes behave in transactional way. That is, the stroke may either complete and put undo information into history, or it can be cancelled. Then the stroke will have to do all the cleanup to revert image into its original state. As you can see on this slide, the user can the developer can either call end stroke, or if the user for example, pressed escape key while doing layer transformation or while doing very long stroke, if the user pressed escape key, we can call cancel stroke, and the image will be reverted into its original state. So all the changes that happened in the stroke will be reverted without first putting it into undo stack and then undoing, as we used to do it in 2010, I think. Anyway, so the fourth API is processing. I think you have heard about it many times as well. Strictly speaking, processing is not a separate API because internally it uses strokes, but it is some wrapper around strokes that lets you process layers in a bit more easy way. For example, on this slide, it's a pseudocode for convert image color space action. You just create a visitor. I hope everyone knows about visitor design pattern. It's a special class. It's a special class that can process different kinds of layers. So basically, the visitor knows how to process paint layer, how to process generator layer, clone layer, vector layers, and so on. So we just call apply visitor, and processing applicator applies this visitor on every layer of the image, and we can instruct the processing applicator to apply this visitor in different threads. That is, if you have, for example, 8 cores in your CPU, the color space of the image will be converted in 8 parallel threads. What's more, a processing applicator allows you to run the visitor on every single frame of every layer. And this is also useful in some cases. We use it for flatten image, for merge down operation, for image transformation. For example, when we need to rotate or mirror the image, we should apply mirror transformation on every layer, on every frame of every layer. We can just create a visitor that rotates a single page device by 90 degrees, and then instruct applicator to apply it to every frame of every layer. I think, as I said before, we have 2 separate queues. The first 2 APIs, the first 2 types of jobs, updates and spontaneous jobs, run in updates queue, and the 2 other jobs, strokes and processings, run in strokes queue. I will tell about these queues more in future slides. So, and the fifth API is legacy actions. We try not to use them we try not to do this, but we still have a few actions that use this way of executing actions in Krita. Basically, you call image barrier lock, do something on the image, and then unlock the image. Why it is called barrier lock? Because it waits all the queues to complete execution of their jobs, and then returns from this function. And when you call unlock, queues can work again. We had a talk recently about Python API. So I think, yes, we have 60 barrier locks in Krita. Some of them I used just to sync the GUI, but yes, we use it. We are ashamed, but we use it. So the first 4 jobs run asynchronously. That is, for example, when you called applicator end, it doesn't mean that when you return from this function, it doesn't mean that the processing has completed. It doesn't even mean that processing started. It means that the processing has been added to the queue and it will be executed sometime later. If you want to ensure that your action has been completed, for example, if you are writing Python API and our Python API is synchronous, so after every end stroke, applicator end, or after every setDirty or ft add spontaneous job, you have to add, I think I can write here, image wait for done. Oh, okay. I think you can see it. So after doing any asynchronous action, if you want to make sure this action has been completed, you have to do wait for done. So that is what we do in many Python API Python API code, but not everywhere, and this is considered as a bug. It is a bit more tricky with legacy actions here. Because theoretically, since you do it synchronously, you don't have to wait for anything. But if the code that happened inside this synchronous block, where do something is written, if this code has called layer setDirty or layer refresh graph from inside the barrier lock, it will add the job, but it will not execute it. So after doing unlock, you will have to call wait for done anyway to wait for the updates. So from Python API point of view, all 5 actions should have wait for done after them. Do you have any questions so far?
Just one remark. This is not about Python. There's not a level where you actually execute Python code. It's when we call into the libkiss library, which can be called from C++ or any other language we bind to it.
Yes, it's about libkiss library. that executes or that implements Python API at C++ area. Yes. Okay. I haven't thought this quite familiar with it. Okay. So the next topic will be I will try to talk about updates queue a bit in more details. All the queues are placed in a class called keys update scheduler, and it has two queues: keys simple updates queue, which is about these two types of jobs, and the second queue, keystrokes queue, which is about strokes. But I would like to talk about updates queue. The reason why we have this queue is not just to make them asynchronous. It does more important job because not all updates can run in parallel. Not all updates can run concurrently. Because of the rule I was talking in the first part, it might happen that you call layer set dirty on areas that overlap. And that's why we need to have a special scheduler that will try to avoid overlapping between different updates we do. It does it in three ways. It may join two updates into one update. It can split one huge update into a set of smaller updates to be able to run them concurrently. Or it may just postpone some updates until no one else touches their area, so to avoid overlapping. So the next slide talks about what happens when you call layer set dirty. So you declared that area rectangle 1 is dirty, so the scheduler should recalculate the projection of the image and show it to the user. What happens next? There are two big steps that happen. First, the scheduler creates a special class, keysMergeWalker. This is something like iterator over layers. So it goes through all three layers of the image and collects information about how these layers should be composed. And this information is rather complicated because we may have filter layers like Gaussian blur filter. We can have clone layers that may try to read from this area, for example, like we ask to prepare this rectangle, but the clone layer will have to read from this area instead. So it's rather crazy, and we should make sure that no one tries to write to this area or in parallel to this update to get consistent result. So when MergeWalker iterated through all the layers and created a how to call it, created a task. Well, yes, it is technically a stack. it is implemented as a stack, and created a task to be executed. It puts this task into a queue, and then when time comes, when the order in the queue comes, the scheduler passes this walker to a class called async merger, don't know. Passes this walker class to this class weirdly named, and this merger class actually composes pixels, writes them into image projection, and shows it to the user. Why is it so complicated, and why we have two separate classes here? Why cannot we do that in one go? And the reason is that they are these two actions executed in different contexts. The walker is created right inside. I think there is a mistake. It looks like this. So the walker is created in the context of the thread that called setDirty. It might be GUI thread or some strokes thread or something like that. It collects all the information and puts it into the queue because it is fast. It is fast to do. And the actual merge operation is done in the background thread and doesn't block the GUI or any user actions. And why this separation is needed? When the walker collects information about merge operation, it also collects information about so-called access rect. This is the area from where this update will read information and where this update will write information to. It is needed for the scheduler to plan the updates later. So we have gathered all this information. Every job has its own access rect and probably reorders them, and to avoid intersections between access rects. So that is, for example, if we have two walkers and their access rects, they do not intersect, so they can run freely and generate the image projection in parallel without any problem. But, well, yes. And if two updates have overlapping access rects, like here, yes, I will answer your question soon. Do you see how I zoom in? Yes. So as you can see, the access rects intersect. So such updates are not allowed, and the scheduler does its best to not allow such updates to run in parallel. So one of the updates, probably Walker 2, will be postponed until Walker 1 finished its execution. And the question from Berhard Liebel. So this is basically a pixel area-based lock mechanism. Yes, it is something like that. This lock is not global. And I should say you secretly that the the algorithm that the scheduler uses is very simple, and it's probably not the most efficient algorithm possible. So if you like to work on it, it might be a really nice scientific task to work on to optimize this scheduling algorithm. What is the criteria for postponing the jobs? Basically, we keep track of what jobs are running at the moment on the CPU, and we iterate through the queue. And if we can add this job to the, if we can run this job with in parallel to currently running jobs, we run it. If not, we just go further into the queue and try to fetch the next one. So update jobs can be reordered if they cannot run it. I think it's greedy algorithm, if talking scientifically. So we just pick the first job, then can be executed at this very moment. That doesn't intersect with any running job at the moment. Better jobs. Better job is a bit a different thing. I will talk about it later, because better job is executed at the context of strokes queue. It is a different queue, so it doesn't. So it. And I will talk about barriers later. Board wine? Should I repeat something? Amy Spark, did you get the answer to your question? Okay. Yes, better jobs will appear on the next slide. Probably right on the next slide. Well, almost on the next slide. Okay, so the next topic is strokes. As I said before, a single stroke is a complete user action. Almost every stroke has fixed init job and finish job. So usually in init job we do some initialization of the action, and in finish job we usually add undo information to the undo stack, and in the middle we just execute something in some way on some CPUs we have. The stroke consists of stroke jobs. Init job and finish job are just special types of these stroke jobs, and we can add as many jobs in the middle. Every job can request image updates. Just call layer set dirty, for example. Here you can see that these three jobs initiate updates, and here I tried to show this borderline between strokes queue and updates queue. Everything here is updates queue. It runs independently from everything that runs here. So, as I said, a stroke is a transactional thing. Either it completes its execution completely, or it reverts everything it has done. That is why the finish. For example, if you started a very long operation, for example, you started converting color space of very huge image, and you don't want to wait for the end, you press escape, and cancel job will be added to the stroke, and it will undo everything that has been done in these 3 initial jobs. Cancel job can also start any updates, obviously. Here we come to the rule of 3. It's a borrowing from old version of C++ language. So if you write your own stroke, you should define 3 jobs for it. You should define init job, a finish job, and cancel job. It ensures that your stroke is transactional. That is, if the scheduler will cancel it because the user pressed escape key, the image will not be left in dirty state. The stroke should clean up after itself. Now let's imagine that the user did. Why cannot I paint? Like the user did 2 strokes on the canvas, like here. So this stroke is this one, and this one is second stroke. Both strokes are put into the queue, and they are and since we are executing them in the strokes queue, all the jobs are in strokes queue are executed sequentially. And important thing about strokes queue is that jobs from different strokes cannot interleave or cannot intersect. That is, any job from stroke 1, well, the stroke 2 will not start until the last job from stroke 1 is completed. I think I have a slide for that. Yes. It may be called a stroke jobs barrier. The jobs from strokes cannot cross it. Well, that is quite obvious, because if you started a painting operation on the image and you probably started a transaction on a paint device, and you don't want to start another transaction on the same paint device. So that's it. One important point about this stroke jobs barrier, it's not a stroke job yet. If Spark, if you want to ask about that, no, it's not a barrier stroke job yet. It's just something implicit that doesn't allow stroke jobs to mix together. And important point about it, it doesn't block updates. This barrier happens only in the strokes queue. As you can see in this image, if you consider this as time, stroke 2 may start its execution before the last update from the previous stroke completed. And this is also intentional, because we don't want to, well, because we want to, well, I don't know how to say that, sorry. It is intentional because when the user makes a lot of short strokes, the updates are running in parallel to, yes, we don't want render of the image to block actual painting, because painting is very calculation intensive. Yes, thank you. So this slide just says that the let me think. What is the next slide? Yes. So yes, break is okay. I was actually wondering if anyone wants some kind of home task to play with strokes, but I couldn't imagine any useful home task, only something easy to play, but not usable for production code. Does anybody want some?
Not me, but I think that if this works out, I might want to give a presentation on the new resource system, say next month.
No.
See whether we can't make this into a sort of institution.
Yes, playing with filter stroke is a good place. And if you go to KISS Filter Manager, you can find a place where add job is called, and if you break it in a way that add job accept intersecting rectangles, then you might get a crash that I was talking in the beginning. I think where it is. KISS Filter Manager, job. So Emmet, I can try to restore presentation. Oh, it's nice. Stop sharing webcam. And how can I share screen? I don't think I can.
There's the button next to the webcam button that allows you to share your screen.
I have a bad news for you. I don't have this button.
Well, I have it.
I also had it previously, but not anymore. Wait. I don't know why. Oh, minimize. Restore presentation. No, I don't have one. Probably I should stop sharing webcam. No. Anyway, so Emmet, if you are playing with filter stroke, you can go to KISS Filter Manager Apply. Actions, take presenter. Oh, thank you. Thank you. That's correct. I can share a screen. Select window screen. Entire screen. Share screen with the sites you trust. Yes, I trust, I think. No. Oh. Okay, so you can see Qt Creator. Here is Keys Filter Manager Apply. And if you go here, you can see that we add jobs and we just pass rectangle. We pass multiple rectangles. We split image area into multiple patches and then pass all of them to the stroke. If you add something like keys grow rect by, for example, 16 pixels here, and run any filter that supports multithreading, you should get a crash. Well, just if you like to play with it. Okay, so it's well, it's just a very old version of Kubuntu. I just changed the how this panel a bit differently to look like Unity, which is dead. So, which is a bit pity. Okay, so should we continue? Volterra, are you back?
I think it's been 10 minutes now, so we should go.
So we were talking about strokes, how that strokes cannot, the stroke jobs cannot overlap with each other, but updates can cross stroke jobs barrier easily. So now I'd like to talk about types of jobs. That is what Amy Spark was talking about barrier jobs. So basically, every job has two properties. It is sequentiality, I'm sorry for naming, and exclusivity. Sequentiality, well, let's first talk about exclusivity. So if a job is exclusive, no any other jobs will run in parallel to this job on the scheduler in both queues. For example, we use exclusive jobs very rarely, but we use it in move tool because you cannot move a paint device while someone is reading or writing to it. It will probably cause a crash. That's why the job that actually moves the layer is declared as exclusive. So all updates are stopped without emptying the queue. Just we stop processing updates, we stop processing any jobs, and we execute one exclusive job. The second property, which is more useful in normal life, is sequentiality, and we usually need only three types: sequential, concurrent, and barrier. I have an illustration here. So sequential jobs are executed sequentially. That is, the next job will not start until all previous jobs completed its execution. Concurrent jobs can run concurrent on all CPUs we have. So, for example, we have two sequential jobs that wait for each other. We have three concurrent jobs which can run concurrently, and the next sequential job will wait until all concurrent jobs have completed. And here you also can see this border line between strokes queue and updates queue. And you can see that neither sequential nor concurrent jobs care about updates. So updates will run in parallel to these types of jobs. And in some rare cases, you want the job to wait until all updates are finished. For example, when you flatten the image, you need to issue updates of normally invisible area, which is outside image bounds. I hope it is understandable. Like layers may have data which is outside image bounds, to the left from the image or to the right from the image. And before merging, we need to update this area so the final layer would have correct information in hidden areas. So one job starts updates of this hidden area, and then we just add a barrier job which waits for everything, for all the updates to complete, and only then executes. Otherwise, barrier jobs behave in the same way as sequential jobs. There is also uniquely concurrent job, but don't think about it. It's used in one place only. What is the difference between barrier jobs and exclusive jobs? There are two differences. First, exclusive job does not wait until all updates in the queue will complete. It means if, for example, I don't know how to paint it here. Imagine this job added a lot of updates, and this job is not barrier but exclusive. And if at this moment of time these updates are not started yet, then instead of waiting for these updates, exclusive job will postpone them till this moment of time. That is, in the end, you'll have update, exclusive, and updates. So the exclusive job will be squeezed in between updates in the current update queue. And barrier job will wait until all the updates have completed. There is also one side effect of barrier job. That is, if you are inside a barrier job and you call setDirty, the update will start right away without waiting until barrier job has completed. So the barrier is actually here, and if you start update here, it will start executing in parallel to the barrier job. And if you can also mark this job as barrier and exclusive, then it will wait. Then it will wait for all the jobs to complete, and update will be started only. Update, it's exclusive. So I think that is all I wanted to tell about strokes. Now I have an example of how we use processings, which are also a subtype of strokes. So here I painted how we do conversion of image color space. As you could see on the previous slides, convert image color space is executed using keys processing applicator class. So on this class you can execute undo commands, processings, and undo commands. Yes. So to convert image color space, we need to do 4 things. First, we need to change metadata in the image object, that now this this image's projection is, for example, grayscale. So we have this undo command. This is set image projection color space. If you go to keys image class, you will find this undo command. First, we need to change projection of the image. Then we should apply processing visitor that converts actual pixels of every layer in the image. You can see it here. It is done using visitor. Then we should do 2 things. This slide is a bit incomplete. We should start updates, because after color space has changed, we need to recalculate image projection. For example, if we change from RGB to grayscale, and we need to emit a signal to notify GUI that our color space has changed. This signal is used by OpenColor.io, profiling stuff, and in a lot of different places. In color selectors, I think it is used as well. So basically, we need to do 4 steps. So the first step is executed as undo command, and this undo command is declared as barrier. That is, it should wait until all updates from previous strokes has completed. This undo command is put into undo stack as a macro, if we well, strictly speaking. Then we apply a visitor on every layer. We declare them as concurrent, so every visitor is executed in its own thread. So we convert layers in parallel in all 8 cores we have. Then we add a sequential job, but in our case it is also undo command. I will tell you why later. It is also undo command. It is declared as sequential. It waits until all layers are converted and starts updates. And technically, there is one more command. Oh, it's a different stylus. Sorry. It's one more command that emits signals, and it is called as barrier. So it waits for updates to finish. Obviously, we should emit a signal that image color space has changed only after the actual projection is ready. So I hope it looks understandable and quite clear, right? Okay, because the following will be a bit complicated. So we have its barrier. We have 1, 2, 3, 4, 5, and 6 undo commands. We have put them into undo stack. We have executed them. we executed them correctly, and we have converted our image color space. Now we want to undo that. I hope someone has already guessed what happens then. Well, the problem is a bit different. The problem is that when we call do, so when the user, yes, they can do undo concurrently, but it is done in reverse order. It means that when the user presses Ctrl-Z, first we will emit signal that image has changed the color space. Then we will mark all layers as dirty and start updates. Then we actually start converting pixels, and then we actually change metadata. Well, we cannot redo this with original config because, we had this proposal to have snapshots of the image, but it is only partially implemented, and we don't use it for actually undo. And yes, we do use comments in this reverse ordering. That's why the next slide will be even more complicated. Well, no, not this one. So to solve this issue, we need to make our action symmetric. We need to so we have updates in the beginning and in the end. We have metadata change in the beginning, in the end. But we change one thing. These comments are not normal comments anymore. They are so-called flip-flop comments, and they have one property, initializing or finalizing. I think Emmet and Ion should know about them because they refactored them some time ago. So instead of undo and redo, these comments have different methods. They called part A and part B. Part A, Owen. Oh, sorry, Owen. Okay. So instead of undo and redo, this comment have part A and part B. So when you want something to execute in the beginning of the action, you put it into part A of this comment, and when you want to execute it in the end of the action, you put it into part B. And the left symmetric part is, you mark it as initializing, and the tail part you mark it as finalizing. So these comments are designed in a way when you call redo, updates comment does nothing. Then set image projection color space on redo sets actual metadata. Then we convert our pixels. Since this comment is finalizing, and its part B is empty, it does nothing. And part B of updates actually does updates and emits the signal. And when doing undo, it does it in reverse order, but this update empty, so it does nothing. Its part A is not empty, so it changes metadata, and we convert the image correctly. I hope it doesn't look too crazy. It might look very disastrous and non-understandable, but the good thing is that half of this work is done automatically by keys processing applicator, so you don't have to worry about it. I mean the updates and signals part. All updates and signals are automatically done by applicator. So when writing convert image color space action, you just need to provide set image projection color space command with part A implemented correctly and processing applicator, and that's it. The final code looks like this. Where is the head? So this code is a bit simplified version of what we have in this image. So here we create a processing applicator. We tell it that we want to process root layer of the image, and we want to process it recursively. That is, all applicators will be applied recursively on all the sublayers of root layer, basically on every layer. We also instruct the applicator that we want to emit these two signals, color space change signal and modified signal. Then we add a comment to the applicator, set image projection color space. We tell that it is initializing and it is barrier, as I told before. Then we add, we call apply visitor, and we tell that we should convert pixels in a concurrent manner. And then we add the finalizing set image projection color space command, which is also barrier. It does nothing on redo, but it does its job on undo. And, well, we call end, and that's it. So the code, I hope the code doesn't look too... well, this is the case when code looks better than the illustration. I think, yes, I think that's all I wanted to tell you, at least what I prepared to tell you. If you have any questions, please.
So, Dmitry, thank you. I think that was a really clear presentation. It was maybe a bit long, but it's a complicated subject with lots of different things in there. So, thank you. Job well done.
Oh, thank you. Thank you for listening for 87 minutes.
So let's try and make a group photo. If you want to be in the group photo, enable your camera. There's a button somewhere. Hi, Bernard.
Hi.
Hi, Amy Spark. Hi, Agatha. Hi, hello, Z. We haven't exhausted Kitty's big blue button instance yet. Hi, Altera. Long time no see. I'm going to take a screenshot. There. That's it for now. Thanks for attending, everyone. Let's see whether we can do something like this again next month. Bye-bye.
See you.